All right, so don't ask me to introduce myself a little bit as well at the beginning, but I'm going to be talking about direct imaging, so this is kind of more of a forward-looking discussion of what we hope we might be able to measure in the future when we have the right instrumentation. But I am the lead of something called the Virtual Planetary Laboratory, which is an astrobiology group. So I actually trained as a planetary scientist, and I tried to, well, I did observe Venus for my thesis, and I was looking for both oxygen and water vapor in the atmosphere of Venus, which is arguably one of the least habitable planets in our solar system, and those were the two things I went after for various reasons: water for the greenhouse effects and oxygen because it was mapping dynamics in the upper atmosphere. But that's kind of where I started, and then I got more into theoretical calculations. And so this large astrobiology group, which is about 75 people across 23 different institutions, works in 5 major tasks where we essentially try to model the appearance of planets we understand, to develop models to model planets that we haven't yet observed. And so we have 5 basic tasks. We look at the Earth as the canonical example of a habitable planet. It will always be our best studied example. We're living on it. We look at the Earth over time to try and understand the sort of different alternative Earths that were habitable but didn't have oxygenic biosignatures on them. We use models to look at star-planet interactions and how that affects the habitability of a planet. And we look at, we have a core of tame biologists who help us to understand what organisms produce and how that might impact the global environment of a planet for detection. And our 5th task is, in fact, this one here, the observer, where we run the environments that we generate through instrument simulation models and retrieval models to understand what we might observe. So that's kind of my background. I'm an astrobiologist, but my background is in planetary astronomy. So today we're going to talk about direct imaging. And so our challenge is one day to find this pale blue dot orbiting around another star, the goal being to try and find a planet more like our own. And I think the study of direct imaging and studying exoplanets in general is driven by 2 major science questions. One of them is in the area of comparative planetology, which is simply trying to understand the context of the Earth and the other planets in our solar system in the larger context of the suite of planets that we now understand. So my overarching question for this one is basically, how weird are we? You know, how abnormal is our planet and our solar system in the larger context of the universe? And that's the comparative planetology. The other one is an astrobiological goal, which is simply to know, are there more organisms out there, are there planets that support life like us? And so that's the question of, are we alone? So to do this, to at least get at the Earth-sized planets, Heather pointed out that that's kind of challenging with the instrumentation that we have available for transit transmission, and because of those collapsed atmospheres, it's going to be very, very difficult. So one of the ways we want to go after this is with direct imaging. So direct imaging, you have to overcome 2 major technological challenges, which I've outlined here. Essentially, you must suppress the light from the parent star so that the fainter light from the planet can be seen. And for an Earth-like planet orbiting a Sun-like star, you have to get down to, the contrast in the visible is about 1 billion to 1. And so to be able to detect these and to potentially do spectroscopy, you're looking at being able to suppress the light of the star from factors of 1 billion to sort of 10 to the minus 11. To do that, we have techniques, coronagraphy and interferometry, that have this concept of the inner working angle or the outer working angle, which many of you probably have heard of. But essentially, that's the inner working angle is how close to the star can you get and still be able to detect your planet and make measurements of it. And that typically goes as 2 lambda over d. So that means that the shorter the wavelength, the closer into the star we can look, and also the bigger the telescope, the closer into the star that we can look. And the reason we want to look close into the star is that tends to be where the habitable planets are. And so trying to push in the inner working angle is a very important part of what we're doing. Now, what I described is true for the coronagraphs and the interferometers, but it's different for the occulters, which I'll just mention in a second. The other challenge we have, though, is not just to suppress the star, but to be able to angularly separate that little planet that's very close to its parent star, if it's in the habitable zone, from that star. And so to do that, we need angular resolution, and that typically goes in the formula. The angular resolution is 1.22 lambda over d. So again, angular resolution improves with large telescopes and shorter lambda. So you can see a trend here that we really want bigger telescopes to be able to do this, which will come as no surprise to anyone. So I'm talking about the occulter. So some of you probably heard of this idea of actually flying a star shade in front of a telescope. In this case, instead of the 2 lambda over d in a working angle that's typical of these other techniques, essentially the inner working angle is decoupled from the telescope diameter, and it's now a function, in fact, of the diameter of the star shade itself and how far away from the spacecraft it's flown. So that means theoretically you can use a fairly small telescope and still get a really nice inner working angle. So that's something to look at. However, of course, the telescope is still a light bucket. You still do need, a fairly good collecting area to be able to do what you want to do. All right, so direct imaging. It's really hard. And you can see here in this diagram, I admit it's a couple of years old. I stole it from Jonathan. Basically, if you look up here, these sort of green things are the planets that we've detected via direct imaging. Clearly, the other techniques are certainly far more productive at finding these sorts of planets, and direct imaging is very hard. And again, it's a function of that, being able to get the angular resolution and that inner working angle to be able to see down closer into planetary systems. So most of the planets found via direct imaging are far away from their parent star, and they're currently fairly large. And they tend to be largely more self-luminous than average, so we look at young, for example, Jupiters in the outer regions of planetary systems. So given that it's so hard, why would we actually bother to do this when we have transit transmission to actually characterize planetary atmospheres? And so one of the, there's a number of different reasons, but one of the key things is that, and Heather pointed it out, is that aerosols can actually severely limit your ability to get down into a planetary atmosphere. And so we can try and pick atmospheres that are not cloudy, but this kind of very nicely shows the difference here. Here's sort of a model of GJ1214b with the high altitude haze in place, seen in transit transmission, and this is the same object, the same model seen in direct imaging. So if we're able to do direct imaging, we have essentially a shorter path length down through the atmosphere. We're able to penetrate deeper. We can not only get deeper into the atmosphere to understand more about what's going on in that atmosphere, instead of trying to characterize the planet from very high up in its stratosphere, but we can also potentially detect surfaces. So that's another principal advantage of doing direct imaging. You cannot detect surfaces or surface characteristics. And if you care about terrestrial planets, you definitely do want to get down there. The other disadvantage that we might potentially have is that because of refractive effects, this is essentially the observing geometry of planet and star with transit transmission. If you are a habitable planet or on a habitable planet in the habitable zone of a G-dwarf, the geometry is such that because of refraction, you can't actually get down deep into the atmosphere. And so on a G-dwarf planet, in the habitable zone, you're really trying to characterize the planet again from the upper atmosphere. For planets orbiting M-dwarfs, and this is shown here, the black line is with no refractive effects. The red line is what you would see for a planet orbiting an M-dwarf, so it's very close to no refractive effects. And the blue line is what you would see for a planet orbiting a G-dwarf. So because of this, it turns out that if you're trying to observe a planet in the habitable zone of a G-dwarf with transit transmission, which again is challenging just because it's further out from its star and so less likely to transit, it's a challenge. So basically what we're saying here is if you care about habitable planets, then the transmission spectroscopy is very good for M-dwarf planets because of these effects, but direct imaging is good for the G-dwarf planets. And so the bottom line of all of that is if you want to study planetary systems like our own, with a planet in the habitable zone orbiting a G-dwarf with a cool Jupiter and so on, then direct imaging is the better way to go than transit transmission. So just summarizing that, again, sort of for posterity on the website and so on, but basically M-dwarf habitable zone planets and close-in Jovians are good targets for transit transmission for all of the reasons that you probably already know and that Heather went over. However, the surface can't be studied, aerosols can severely limit the altitudes probed, and transiting planets are rare and so further away from us on average. So if we want a nearby planet to study that's very nearby, you would like to not have to rely on getting a transit observation. Direct imaging, on the other hand, is going to be great for getting images and spectra of planets, again, more like our own. And so finally answer that age-old question of just how weird are we overall. And we can also potentially obtain direct images of the planet itself so that it's not necessarily having to be in transit. We can measure the planet's brightness as a function of phase and obtain spectra on that. And we can probe the atmosphere and surface because we're less affected by haze. However, the bad news is we can't determine the size, which is probably going to plague us in the end. And the bottom line is the technology to detect and characterize these planets is not yet available, although we are certainly working on it and getting closer. And so to that end, talking about the current status in ground-based systems, we are in fact observing planets directly from the ground with a bunch of instrumentation here on ground-based telescopes. The systems are taking an approach that's very similar to the high contrast imaging from space using coronagraphy, but they're limited to contrast ratios that are sort of this order, which is good for larger or self-luminous planets away from their parent star, but not so good for habitable zone planets in close. This, I'd like to show this one. This is sort of Jeep high, getting some of the initial spectra of these objects that orbit around the star, sort of Jovian-type planets. And we showed this at DPS, and basically people have not been able to fit these yet. So even with our very first direct imaging spectra here, good spectra, we're still confounding models. We're finding these planets are smaller than they're supposed to be based on evolutionary models, and so we're still pushing the science with this. So just to do kind of a comparison, for the ground-based direct imaging, we're kind of here on this diagram. Here's our ability to separate the planet from the parent star, that angular resolution. Here's that star-planet contrast, being able to suppress the star. Here's the mirror diameter we'd really like to have, but here's the ones we kind of have for different types of missions, yeah, just differences in magnitude over here. So here for the ground-based, we're kind of floating up here at the 10 to the 6, 10 to the 7 type of contrast, looking at sort of an arc-second or sub-arc-second separation. What we'd ultimately like to have is to be able to observe something like the Earth, and I took this from the XOC proposal, and there's sort of our sensitivity curve on there. And you think, well, okay, so it looks like XOC can only do Jupiters, but this diagram was developed for planets at 10 parsecs. And so if you were actually able to take the solar system and put it more at 5 parsecs, then these planets would move into this region here, and we would actually have a chance of potentially observing those types of objects. So there's a series of direct imaging missions that are being planned, and so you probably saw this diagram from Gary early on, but we're over here in this region, W first after C, and then some murky thing in the distance that's not quite able to be discerned yet, but something that we will eventually develop. But people are working on concepts for all of these things. So the one that will mostly likely fly first, W first after C, it's an internal coronagraph. With its sort of baseline specs, it kind of intersects in this area of the what planets can I get diagram. Up here, you've got things that are fairly massive. Down here, the blue things are the things I care about, so these are sort of terrestrial-sized planets. If we can push goals on W first, we'll start to get into this particular region of the diagram. But it's unlikely that these terrestrial planets are going to be potentially in the habitable zone of their parent star. They're probably going to be closer and brighter for the contrast. On the ground, though, people are working away feverishly at various technologies in the coronagraphy to see if we can get down to what we need. And at least on XOC, we looked at the hybrid LEO coronagraph technique, which is really pushing down to the sort of contrast ratios that we would really like to see, but at the moment over fairly short bandwidths. And we would like to have coronagraphy over larger bandwidths so that we can do spectra in an efficient way. So I'm going to talk a little bit briefly about sort of examples of the sorts of things we might try and observe with these types of missions. So XOC I'm talking about, not because I think it's absolutely the best, although actually I do, but I was on the mission Science and Technology Definition team, so this is the one I know best. So we brought it down to a 1.4 meter telescope with an internal coronagraph. We hope to be able to do filter imaging and R equals 70 spectroscopy over 0.5 to 1 microns. And so we're going to look at what sort of science we could potentially do with that. So one of the things we did focus on for XOC and is kind of one of the jewels in his crown is we designed it, this is a concept, not necessarily going to fly, but we designed it to be able to actually null out the second star in the Alpha Cen system. And so we could potentially look around one of the stars in the binary. And so these are simulations of basically a 5-day integration in V-band, being able to get an Earth-sized planet in the habitable zone of Alpha Cen A, and a disk average spectrum of the planet in about 28 days. And that's what we were showing up here with the noise model in place. So that would be pretty fantastic. But you can also see the other sorts of spectra that we would hope to get, Jovian planets and mini Neptunes as well. So how much time do I have here? 11 minutes. 11 minutes, okay. So For the Jovians to Neptunes, we have some very basic science questions, and maybe Doug won't think these are specific enough, but we have these sort of big picture questions of what we'd like to do with this type of instrumentation. And that is essentially look at how the composition of the gas in the planets that we observe, because we'll be able to get spectra for both the gas and ice giant planets, how does that vary with planetary mass, orbit, and stellar mass and metallicity? So just trying to understand, again, this context and this comparative planetology question. And what does this tell us about their formation and evolution? And of course, fundamentally, that thing that sort of dogs us in transit transmission is how do clouds affect giant planet atmospheres and vary with temperatures and other planetary parameters, since we have a better chance of getting down through them. So direct imaging will allow us to obtain images and spectra of Jovians like our own. That's, again, the takeaway image. Not hot Jupiters that are close to their star, which is what transit transmission gets us, but cool, average, normal Jupiters, or at least we hope they're normal, sitting out in their planetary systems. We'll be able to observe a bunch of gases, methane, water, ammonia, possibly hydrogen in some cases, and some sodium and potassium. Measure the presence of clouds and cloud heights, go after cloud thickness as a sense of getting us planetary temperature, and to search for Rayleigh and Hayes scattering. So Heather mentioned this as well, but is there a correlation between metallicity and mass? Is it true that the smaller the planet, the higher the metallicity? We can kind of draw a line through our solar system, but is that necessarily true of all other solar systems? And of course, getting a few extra points here would be really kind of useful. Also, clouds will form, different clouds will form as a function of temperature for these Jovian planets, and it would be great to be able to get spectra and also to try and understand the clouds more and where they form. And this diagram is actually showing effective temperature of the object, sort of based on its distance from the parent star, and its mass from radial velocity. So these are all known radial velocity planets. The solar system planets actually sit in here. We have sort of ammonia clouds around Jupiter and Saturn, but there's certainly a huge spread in even the known RV planets in the sort of exotic clouds that we might be able to see with these sorts of missions. And then ultimately, we want to try and get R equals 70 resolution spectroscopy of these objects. And this slide is basically just to show that depending on whether you have a cloud, what it's made of, and where it is, it can create quite a diversity of spectra in the Jovians. And so we hope that because we're sensitive to these things in the spectrum, that we'll be able to learn more about them. So just to quickly show that, here's sort of this idea. You can have either a high cloud up here with a short absorber column abundance above it, and so you tend to see weaker features. Lower clouds, you can end up seeing deeper features. And this is an example that Mark did, Mark Marley. Essentially, red is real Jupiter. That's the Jupiter we know and love. This blue here is one of Mark's initial attempts to actually fit the spectrum. And you can see that he's getting fairly close on abundances, but we're kind of not right here. What this is telling us is that, first of all, bottom line is we can measure the abundances of methane in here. We can see the absorption lines for methane. We can also look at the continuum, which tells us whether we've got our cloud in the right position or not. We can play around with the cloud position in the atmosphere to see whether we can match that spectrum. There's also here, basically, and also up in here, a weak absorption from water vapor, which is something we'd be very interested in seeing in the Jovians as well. And perhaps if you are a spectroscopist, you'll notice that the place we're really having a problem is over here, where on Jupiter at least we have this turn down, this absorption in the spectrum, and in our test planet we do not, and that is due to a high hydrocarbon haze. So this particular model does not contain that high hydrocarbon haze that's doing the absorbing. So the fact that we have this discrepancy would let us know that probably a haze like that is present. Finally, on Jupiter's, just I want to show that hopefully you all know this, but resolution is really important. So these are simulations of Jovians, essentially done at a bunch of different spectral resolution. What I want to point out is there's a wealth of information in here, and over here, not quite so much. When we see R equals 10, you can see the loss of the absorption features, and also the fact that if we were to even sense that maybe something was going on here, we'd have to have a very good signal to noise to be able to discriminate between these. And I also want to point out that when you're looking at spectral resolution, sometimes it's not just the absorption lines that are narrow. The actual continuum becomes the narrowest part of the spectrum. And sometimes being able to identify the continuum actually drives our resolution. Okay, so for sub-Neptunes and terrestrials, we have the questions you might expect. What are their compositions of the sub-Neptunes? Basically, what the heck are they? We have no example in our own planetary system, and we'd love to know exactly what they are, except some of them at least seem to be covered with high hazes, so we're not learning that much at the moment. but we also hope to, again, get spectra of terrestrials orbiting stars like our own. And these are the sorts of things we would go after in the measurements. So we can search for surface inhomogeneity. We can search for, whether or not we can see continents or oceans, or at least different colored patches on the planet. To search for an ocean, to measure atmospheric constituents, and to measure the presence of clouds and aerosols in the atmosphere, and also to try and do temperature and pressure determination. So in the last little bit here, I will try to talk a little bit about what we might do with those. So this is actually riffing off a technique that Heather originally did, but looking at essentially time-resolved multi-wavelength photometry. Heather was talking about doing sort of phase-dependent measurements and being able to map different regions of the atmosphere of the planet as you did that, because you got to see different views of the planet. But if you have a planet rotating underneath you as well, then what you can do is essentially take light curves of that planet. Now this planet you should recognize, it's the Earth. It was actually observed by the epoxy spacecraft as if it was a distant planet. We took time-resolved light curves of it in different filter bands. And we were able to use pretty simple PCA analysis to actually pull out some fundamental spectral components of the color change of the planet. These are the eigenspectra. There's a red one and a blue one. Actually, when Nick did this, there was a black one that behaved like this. And he threw it out because it only counted for 2% of the signal. And I believe that was actually the vegetation red edge signal he was picking up there. But since he could explain 98% of the color variation without it, he threw it away. So, but that might have actually been life in there that we could have been looking at. But anyway, but the point is with 98, with just these two eigenspectra, we can explain 98% of the color variation on the Earth. If you transform that into a map of the Earth, you are essentially identifying where there are redder areas on the planet, so these are the continents in this case, and where there are less red areas are the oceans. So basically take that lack of spatial resolution. If we can actually get temporal resolution and we have a rotating planet, we might be able to map spatially. The other thing we would want to look for are oceans. And so we can use the Glint technique essentially. Obviously we wouldn't have spatial resolution, but if you were to put your planet in an entire pixel, as that planet gets towards crescent phase, you will observe the specular reflectance, which is sort of this mirror-like angle of incidence equals angle of reflection phenomenon coming off any liquid bodies that are on the planet. So this is actually specular reflectance or glint from a lake on Titan. And so we've seen this in the solar system. We have run models of this for the Earth. And what I just want to show here is this is the Earth's basically apparent albedo. So the albedo a Lambertian sphere would have to have, if you assumed isotropic scattering, this would be the albedo you would need for your Lambertian sphere for the Earth as it goes through its phases, from full phase to crescent. And the bottom line is if the Earth behaved like a Lambertian sphere at all phases, then you would see a straight line on this diagram. But you do not. If you look at this bowl-shaped curve here, what happens is that, in fact, we deviate very strongly from Lambertian near crescent phase, and that is due to the effect of both clouds in the atmosphere and also the effect of our ocean. So we've since actually validated this technique using actual observations of the Earth taken by the LCROSS spacecraft. Can you all spot the ocean on this planet? Right, it's pretty obvious. So imagine that in one pixel, and imagine that it doesn't behave like that at different phases, and that's the sort of measurement we would like to make. So we actually calculated, we figured out sort of for our canonical object at 10 parsecs, we probably couldn't do Glint. And we said, well, why not go for gold? Let's say we have a habitable planet orbiting around alpha Cen, and we looked at sort of the integration time we would need on XOC, which could do alpha Cen. And if we were to observe sort of where the crescent phase Earth is at its brightest in this wavelength region here, if we got an observation near dichotomy, near quadrature and near crescent phase, and we would have the angular separation to do that for XOC, we could potentially with, 10, 20, 30 days of observation look for oceans on a planet orbiting alpha Cen. And then just wrapping up, because I assume I'm running out of time, other things we might like to do. Just want to point out that molecules, when they're in dense atmospheres, can collide and form collisional pairs. So you always think about oxygen as being something we should look for. Oxygen, though, also creates these dimer molecules, these collisional pairs. And those dimer molecules are more pressure sensitive to the monomer, the oxygen you're breathing right now. And so it turns out if we can get into the near infrared, there are bands from these dimers and also composite features here, such that the behavior of the monomer is pretty flat with pressure. So this is the pressure of the planet's atmosphere going up. But the dimer behaves massively differently. And so if we can ratio those two bands, we might be able to go after pressure determination. but we'd need to be in the near infrared. Also in the near infrared, there are a whole bunch of other molecules. I was pointing out at lunch today that one of the reasons CCDs are built over here is because our atmosphere is so transparent. That's where astronomers like to look out and observe. But for a terrestrial planet, that's a very boring region of its spectrum because there's not a lot of things observing down there. So you really want to get out into the near infrared where we have essentially another bunch of molecules that could help us out, CO2, methane. And essentially we might need these to try and determine the greenhouse effect on the planet that we're looking at, because we don't have any missions planned that contain direct thermal imaging. All right, so I will finish up here because I'm eating into my question session. So again, just spectral resolution again, more is better. And if you're trying to detect the oxygen A band in particular or the continuum on either side of it, we really didn't want to go below a resolution of about 50. So just wrapping up very quickly, looking for oxygen. I just want to get across the point that if you are a cyanobacterium and you and your billions of friends have been around for billions of years, you can severely modify the atmosphere of your planet. And in fact, they have done that, and you can thank them for the oxygen you're breathing right now. So oxygen is probably the first biosignature we're going to go after. And I just want to point out that a lot of people say, well, surely humans being larger or elephants or whatever would make a much bigger impact on a planet. But we don't. It's the microbes that will actually give us that signal. If you want to know what kind of a signal we make in our atmosphere, there's this thing, which if you had been in the monitoring station in the basement of the science center in that building in Alpha Centauri, and you had been watching this planet for quite some time, this Earth thing, you might have noticed, in the last few hundred years that there'd been a massive spike in carbon dioxide. But you would have to be monitoring for a long time. And so that's our rise here. When I got my PhD thesis back here, it was like 360. So even in my lifetime, it's been massively rising. This other thing, this is also a signal of photosynthesis. It's carbon dioxide phase on our planet. And I'm finally going to finish up, otherwise Dawn's going to take me down here. So I just also want to point out, and there's something I can talk about later, but my team has now worked on looking at false positives for oxygen, since oxygen is so important as a biosignature. And we have found 4 different ways to make abundant oxygen in the atmosphere of a habitable zone planet via its interaction with the parent star and its planetary properties. So oxygen will need a little bit more extra care, and the answer to this we're currently working on is trying to figure out what else we need to observe to discriminate between these other false positives for oxygen. Finally, we just did a sort of quick at-last simulator. That's really what I want to see one of these days. But I'm going to need an 8-meter class mirror at least. And I will finish up with a really general summary, which is that, hey, direct imaging is needed to characterize other planetary systems like our own. If we can observe Jovians, we can learn about their nature and formation. And of course, direct imaging will finally get us a planet like our own and help us know what our place is in the universe and whether we are in fact truly weird. Okay. And I'm being taped, right? So.
Summarize that.
Oh yeah, so I summarized this. So the summary is that there's sort of 2 schools of thought in how we should push forward for a mission for exoplanets. One is to put a coronagraph on a very large common user telescope and sort of get our other communities on board in helping us get that telescope together. And the other is to have a more dedicated off-axis, maybe smaller coronagraphic telescope that's dedicated to exoplanets. And the question is, what is the thinking about this, I guess. Yes, that's kind of a really big debate in the community at the moment. The question was, what is the dream mission? I think this is really politically fraught. And so I think, and the bottom line is we as exoplanet observers could probably do a heck of a lot with a 4 to 6 meter telescope that was dedicated to what we wanted to do. Whether or not we could get our colleagues to sign on to that and not start sort of World War III in the community is another question entirely. But it's interesting because I've heard the cosmologists say that they basically won't get out of bed for anything less than 8 meters. And so that's what they want. And so they would see potentially us doing a 4 to 6 meter as a threatening thing, taking money and time away from the ultimate goal of building this larger telescope. I think, because I'm being taped, that we could do really well with either type, right? So the point is, but I think, having a common user, larger instrument, from the scientific standpoint, if it gets me out into the near infrared, if it gets me sort of more of that science that I need to do, then yes, I would be behind that. There's a danger perhaps with a smaller 4 to 6 meter thing that we would maybe skimp a little on the capability. So if we had a more capable, larger telescope that we had to share, maybe that's advantageous compared to a dedicated thing. But either way, I think we could do something with either one of those. I'd be happy. Scott.
So,
Okay, so trying to summarize what Scott said. So he was saying that there's also a trade-off potentially between the coronagraph and the starshade as to which one would be better on this type of smaller mission. I would just add is if we're talking about dream telescopes here, I would have to have both flying together. I would like to have EXO-C with its versatility and multiple visits, and then I would like to bring EXO-S in whenever we're looking at a close inhabitable zone planet and I need that in a working angle. And since it has a limited number of moves, we'd use it on the very best targets that we wanted to go after. So that is certainly a debate. But then the other issue is with the smaller telescope, 4 to 6 meters, maybe we could get more community support by bringing in an ultraviolet component that would bring in more of the community that would not be getting potentially another mission after Hubble that would have that capability. So yes, I agree with both of those points.
That is interesting or useful.
Oh, yeah, absolutely. And I didn't mention that. It is, it's kind of a form of direct imaging, but it's also going to be done in transit transmission. But the Snellen et al. Idea of having this ultra-high resolution spectrograph that even in transit transmission could separate out the lines of, say, oxygen air glow or oxygen absorption from a planet, that's fascinating. And that's something we can do from the ground, potentially. So yeah, that's another thing.